others here. So I give a proof, but I want to reprove it because the language I used before is something I want to discuss before using later on. But just I want to repeat this remark that the language I used is actually very useful, and you'll see this. But here's the phone. So first of all, let me write it down. I did say it earlier. Enough to assume and enough to deal with this case. So is this clear?
Can you repeat that, please?
So we do. Now for this case. And consider assume age is the last or the first term in the composition, in the defining the composition series. I guess it should be a composition series should not be unique, but there is one that, because of its existence, our group is split, right? So I'm taking H to be a normal group. This is a K subgroup, and this is a K isomorphism with GA. And so assume we do know it for this case. I mean, we do know that this guy is not empty. So this is by the reduction. So this set is a compact subvariety or subset of VK, which by normality of age, which is GK invariant. So age is normal in G, HK is normal in GK. It's GK invariant, and on which GK acts via a lower dimensional subgroup. Hence, now I'm using induction on dimension. I will have, on this set of fixed point, I will have a point fixed by this. So this is the reduction. The reduction uses induction. So I will have okay, so I do use, I do consider this case. And now I'm take x in x such that Gx has a minimal dimension. Minimal among all other x's. So Gx, to remind you, is a subvariety. Now I'm not considering k points. This is a subvariety of V. And as such, I mean, it's locally closed subvariety. As such, it has a dimension. And I'm taking such a guy that the dimension is minimal. Then look at the boundary of this variety, and since on this boundary the G orbits are all of lower dimension, right? If I have an orbit, the closure of an orbit consists of finitely many orbits of low dimension. So the boundary here consists of orbits of lower dimension, so it cannot intersect x by the defining property of x. That is, if I'm looking at, or therefore, look at the k points of this orbit inside x is closed in x. It's, if you wish, it is a risky closed in x. If you take x with, there's a risky topology. What we said here, that this is induced as a risky topology to x, and this is a risky closed. In particular, it is k closed. So when I say closed, usually I mean without the adjective Zarinsky, I mean the K topology. A priori it is Zarinsky closed, hence K closed. Hence, in particular, for the K topology, it's compact. The house of K topology, hence, now, or maybe not hence. Oh, here's the general. GKX is closed in the variety, right? So here's an homogeneous variety. This is the k points of an homogeneous variety, and this is the GK orbit of a certain point in it. And this is we spend quite time on proving this. The orbits, the GK orbits are closed, right? And for homogeneous varieties, we get, combining these two facts, we get that GKX is compact. And now, again, in a similar way to the way we described it earlier, we consider this orbit, what I mean, the dimension of this orbit. We have two cases. If stab Gx is zero-dimensional, so this is a subgroup of G. G now is one-dimensional group. This subgroup, the stabilizer of X, is either zero-dimensional or one-dimensional. If it is zero-dimensional, then the orbit itself is one-dimensional. If it's zero-dimensional, it is finite. Then GKX, the same GK modulo some finite subgroup, the K points of the stabilizer. this is homeomorphic. Isomorphism is on the level of topology because orbits are locally closed. We know that the orbit map is a homeomorphism with the course of space. But this guy is not compact. Also, if I divide by a finite thing, it is not compact. Contradicting this one. Is not compact. Contradicting the if part. Hence, stub gx is one-dimensional, and the orbit and gx is zero-dimensional. Since G is connected, so this is a zero-dimensional connected. Gx is this point. Is a point. And x is G, and in particular gk fixed. Okay, question? And
Is the characteristic zero?
no, here I didn't use characteristic zero. What
You need that GK is not compact.
GK, well, yes, but GK, or in this case, G is GA or GM, is either the multiplicative or the additive group of the field. And this is the case also for, say, FPT.
Ah, no, local fit.
Okay, I mean, what is...
No, I was thinking about finite fields.
Okay, for finite fields, all these compact, everything is compact for finite field. Actually, finite. You can look at the k-points. Right, so...
Why is the algebraic argument simple? It looks...
Oh, it's pretty much the same. Somehow, in the algebraic argument, you don't have... there is some delicate issue that here... I need to look actually at closed orbit. Orbits in an homogeneous variety, orbits are closed, and which I didn't need. So this is something a bit more delicate, which didn't come about for the algebraic arguments. Then only locally closeness of the orbit was needed.
So it can work for something like
So yes, so there are other situations when this is really crucial, not here, but somehow this was an extension. You don't need it. In any case, it's quite simple.
I'm a little confused. You ended up proving that gx is a point. So doesn't this mean that x is g invariant, not only gk invariant?
Actually, if you think about it, since gk is the risky closed in x, if x is gk invariant, then it is G invariant. But I didn't formulate this in this way because most of the time, in such situation, I don't care about it. X to begin with, I didn't assume to be G invariant. I didn't assume X to be a subvariety here. So it is more general. But I guess, I hope that for most of you, this fixed point theorem it looks quite familiar. There is a version of this which works in a higher generality, not of local fields, but in general for every algebraically closed field. Replace compactness by completeness. You know the notion of complete variety? Did I discuss this in this class? I don't remember. So, a complete, I think I remarked about it last time. So there is a notion of a complete variety, which is which behave algebraically, geometrically, as a compact variety. X is complete. Now this is a variety over algebraic closed field. What I'm writing here is just a remark. X complete, use definition, if x times y to y is closed. It's a closed map for every y. So this is a property that defines a compact topological space within the collection of all locally compact Hausdorff spaces. This would be could be a definition for compactness. So you can use this definition to define some algebraic geometric property, which you call completeness, and now forget K, forget the notion split. You have the fixed point theorem says that if G is solvable, connected solvable, then for every action of G on a complete variety, you have a G fixed point. This is Borel fixed point theorem. And
So because GA and GM are not complete?
because GA, GM are fine. So what you would do is exactly without looking at the delicate thing of K points, etc. You just imitate this proof, and eventually you will get this dichotomy under this orbit. This orbit is 1 point. I mean, it's 0 dimensional, ends by connectedness 1 point, and you're done. Or you will get it is such a variety, and this variety should be complete on one hand, but it is an affine variety on the other hand. And it is known that there is no map, every map from a complete variety, connected complete variety to an affine variety is constant. So this is one of the basic theorems of algebraic geometry, and by this you get this contradiction. Here we contradict compactness. There you contradict completeness. But the same proof works, and this proof is very famous because it uses. So let me again remind you this without writing on the board. These are things that you should know, but why not repeating? You use this proof in order to show that all Borel subgroups in a given algebraic group are conjugated. If you have a reminder, I'm about to write down a similar thing, or maybe a Borel subgroup of G. Now there's no K signs here. It's only about it's over algebraic closed field. Every Borel subgroup of G is so this is not part of my lecture. Just practice is a maximal connected subgroup of G, algebraic, of course. Otherwise, it might be self-correct. Subgroup, thanks. And a parabolic subgroup is, say, P in G, such that G mod P is complete, equivalently. Projective. For homogeneous spaces, the complete being projective is the same. I didn't say it. Projective, when in our situation, projective variety is compact, but K points all. In classical situation, projective varieties are always complete. Not all complete varieties are projective, but this is really some. There are bizarre things, but most sort of projective varieties, certainly all homogeneous projective varieties, all complete varieties are projective. Now, P will be is called parabolic if G mod P is projective. This is the definition, if you wish. And the other term, the following defining term for Borel subgroups is all Borel subgroups are conjugated. G mod B, or B Borel. Then, or B parabolic. The Borel is parabolic. We say the Borel. It's well defined up to conjugation. And each parabolic contains a Borel. How do you prove this? Exactly. Okay. Maybe you could think of it, and you will see the proof if you don't remember it. I'm about to prove a parallel theorem for split soluble groups and replace compactness by completeness. So the proof that I'm about to present is pretty much an analog of the proof, that one. Okay, the proof that I'm about to present in characteristic zero. Because, well, I guess I'm about to use, there is an obvious thing here. Every triangular group is soluble, right? Which I will use, you would use while proving this one. And we have the analog of that in characteristic zero. Every connected triangular group is split.
And that works only for local fields if we don't.
Well, when I use compactness, everything just, over finite field, everything is triviality. Over bigger fields, well, it doesn't make sense to discuss those things for non-complete fields at all.
No, but the statement you just said, that every triangle, what you're multiplying.
No. The statement that triangular groups, connected triangular groups are split, this is true for any field of
you said you need this theorem.
Well, now I'm about to present a theorem, which is an analog of that, using that. The proof will use that. Okay, maybe. Then, if something is not clear, I will be happy to answer. No? I'm back. K is a local field. Let G be K group. Then all maximal split this connected soluble subgroups in G are conjugated and actually K conjugated. If age is such, then GK mod HK is compact. Okay, so this is an analog of that. subgroup such that GK mod LK is compact, then L contains such a group. Again, such, I'm just too lazy to write down.
So number one here, there are fields that it won't be correct?
No. The theory is correct over any local field. Okay?
No, but when,
The proof that I will present will require that the heuristic is zero. Okay? And I will.
yeah, my question is, what if K is not even local? I mean,
If it is not even local,
so,
then typically constant spaces will not be compact.
yeah, but number one.
No. So sorry. Number one will be correct.
Okay, with different proof.
With a different proof. Yeah, this will follow from prototype theory. Yes. Number one, which has nothing to do with compactness, is still correct, but you will have to define you will have to develop another tool. Yeah, which I will not do right now. Maybe we'll go back to it later on when we will discuss what is. Yes, three which relate to compactness are just more or less meaningless over fields which are not local, and the true meaning of one of a local field is actually related to compactness. Okay. Yeah, but it's certainly a good question, and I should be reminded about it later on. Okay, so I'll start now a proposition which it is a lemma. It's like a subtheorem. So the proposition is there exists L. I mean, under this, there exists L in G such that there exists such L. Such is our shorthand for this long sequence of adjective, such that GK mod LK is compact. So 2 says that every such group has this property. So the proposition says just that there exists H with this property. Okay? So this will be an easier thing to prove, but actually enough. And what I'll do now, I will have 2 steps proof of the theorem. I will prove the implication, proposition implied theorem, and then I will prove the proposition. And the proof of the proposition I will give only in characteristic 0 in a complete way. Okay, any questions about formulation, etc.? Okay. Okay, let's start with 3. I think this is the easiest. This is actually this will follow from the fixed point theorem, which we already had. For any such H, so what? Actually, maybe I'm proving more than 3 because I didn't prove 1 yet. I don't know that they are all conjugated. I will prove 3, which there's no point in writing down because it's a subcase of 3. For any such H, and any L with this property, L contains a conjugation of that H. Okay? For any such H, consider action on GK mod LK, it certainly sits inside G mod L K. This is VK. V is G mod L. And this is compact. And certainly GK invariant. My FPT. So this is X, right? Okay, I'm done. X HK is not zero. Hence, it means that some conjugation of L contains H, or L contains some conjugation of H. Hence, L contains a conjugation by this attribute, a GK conj of H. So again, I proved a bit more than speak. I proved it for any H. Now one. So what is that I want to prove? Now I want to claim that for any H, for any such H, this is compact. I do know that for some, I do a superproposition, right? I do know that there exists such an L, such an L, which is compact. So fix any such H. Fix L as in the proposition. By 3, which we already proved. We can find this guy such that AG is in M, or AG in LG. Doesn't matter. But this conjugation of L is split solvable, connected. H is maximum, split solvable, connected. By maximality of H among whatever H is. So this shows that I can conjugate any group, any such group to L. In particular, they are all conjugated. 3 follows. For that, L is one fixed guy here, which I took from the position. Okay. And now, 2, I want to show. Oh, sorry. What did I do? I mean, I did everything. Okay, but then the argument I just gave was already.
No, that's okay. 2 is just immediate now.
Yeah, 2 is immediate, but what I said at the very beginning, I forgot. I want to show that. Oh, sorry. 2. 2 things. 2 immediate. Of many. GK on HK is the same as. Okay. Fine. Okay, so we still need to prove the position. Oh, but the same goes here, so maybe I should not erase this. Shall I or shall I not? So, given a similar proposition, I want to remark what I'm doing on that. So if I would be able to prove that there exists one Borel such that G mod B is complete, is projective, this is the analog of the proposition, then that theorem will follow as well. Okay? So now, proving the proposition, you should also think how similar proof would give that some Borel is projective. Yeah. Okay, I don't. Okay, first of all, I'm putting my G inside GLV. I can always do that. And let X be the full flag bracket of V. Fix X in X, K point, with Gx of minimal dimension. So the boundary here consists of orbital flow dimension by the minimality of dimension. The boundary is empty, is closed, hence compact, hence GKX I should now say aloud again. This is not a complete triviality. What is triviality here is that Gx is a projective variety. Gxk is compact. Gkx is compact because the Gk orbits are closed in that homogeneous variety, Gxk, right? This is something we struggled to prove earlier. We used it once earlier, we used it again. I will not make this remark again and again and again, but I do want to emphasize it. We worked here. We worked to get it, so we deserve noticing that we did something. Now, say, define L prime, this is not my L yet. I want to establish a certain L, right? I want this L. My L will be the connected component of L prime. So I'm starting by taking L prime to be the stabilizer in G of that X. L will be the connected, this symbol is for the connected component of, right? Now, GK mod L prime K, if you that, right? Is compact. L prime K mod L K, this is a subset of L mod L prime. Okay. This is the final rule. zero-dimensional group. Hence, GK mod LK is fine. So the struggle to move from N prime to L just to be is thanks. So I want it to be connected. So, with the last line, L is connected and triangulated, triangular, lines, given char is 0. That is good. And L is such. Well, that is everything we need to do. Right? And I'm done. In the where I would prove this one, I would deduce here that L is a point. And in particular, that G mod L is compact, or G mod B is projective. Okay. Now, any question? So everything is quite easy. Something hard here, but the proposition, as I did say, or did formulate, it has no requirement about the characteristic. The proof that I did need answer the characteristic to be 0. So I want to make a remark on the proof. In characteristic P. Again, I assume that most of you don't care much about it, but for completeness, I think it's really very interesting. And moreover, I couldn't find it in any book or any text or any article, those things. So if one of you wants to write it down, I think it was it is certainly known, but I don't think it appears in any place. So it is worthwhile writing this down carefully and maybe publishing. So if any of you have time and energy, I would be happy to assist. So in characteristic 0. So how long did you get without a characteristic assumption? Up to here. We found that we can find we found a triangulated group, triangular group, connected one, which is co-compact. Now we just want to show that in this guy we have such a group which is co-compact. So we can replace G by L. Right? So we can ask about this proposition starting with L being triangular group. Take L to be a triangular group. Prove that it contains that one can find another guy which is connected and split and solvable. Well, the solvable comes from free and compact. Okay, actually prove that a maximal split subgroup of a triangular group is co-compact. Now, it is clear how to reduce the question to any subquotient of L for the compositions, the obvious decomposition series. Right? So the only thing that you easy to reduce the question reduce to the question every. So if I'm taking and again by the way, so if L was triangular groups, then we looked at a certain decomposition series of triangular groups, and the only place where we had problems in positive characteristic are for unipotent groups. What you reduce is, so you take a unipotent group in the decomposition series, so you may assume it is a billion, and you may assume that you divide it by whatever split subgroups that you found in it, right? Because they all fit inside such a group. So you end up having an anisotropic group, something that has no split group. So to the following, every unipotent abelian anisotropic group. So this is something that cannot live in characteristic zero, unipotent anisotropic, unless you trivial group, right? By the fact that we've seen that every unipotent group splits. Group is compact. And this is a theorem by one. It's not so hard theorem at all, but I will not prove it. I will just, I'm trying now to reduce it to known. Since this does not appear in the literature, as far as I know, I wanted to reduce it to something that does. So this is a complete proof. Questions? Take S to C. Okay, so SL2C act on the projective line over C, which is the Riemann sphere, right? So it acts on S2. Moreover, it acts on, so it acts on T S2, the projective, on the tangent bundle to S2, and on, let's call it, I'm not sure what's the name, DS2. So take, I'm doing a canonical construction here. At each point of S2, I'm having a tangent space, and I'm taking the bundle of the projective lines associated. So maybe I can identify, well, SL2C does not preserve any Riemannian metric on S2. It acts conformally, not isometrically, right? So it does not preserve the unitangent bundle to S2, but it does so projectively. So whenever I move this point to that point, I move tangent plane here, changing conformally the tangent sphere projectively, of course. I'm preserving things, and this is, of course, this is a compact bundle over this compact space, and which is compact. And the action is homogeneous, or transfer. So I want to explain what is a stabilizer of a point here. So when you act on here are 2 by 2 matrices. If I'm looking at this Borel subgroup, as you all know very well, if I divide it by this Borel group, I will get P1C. And now here you see this is a copy of C. You know, this is the additive group, and here you have C star, and this is GL. Now I want these to cancel out. Together they form C star group, right? diagonal group is SO2 times R2, of course, R star. And I don't need this. It's enough for me to take here lambda inverse, lambda real. This would be, so again, I don't know if you know this Lagrange decomposition of parabolic groups. Is this familiar that every parabolic group is written like MAN? Anyone saw it? So usually for the minimal parabolic group, for the Borel, those things that I think I will go and discuss in more details. But those are the classical things that I have.
What is A?
A
No, MN. the Nilmotons and the Levy.
will be this one. M will be this one. N will be this one. So there is a canonical or standard decomposition of those parabolic groups, and they contains some Levy thing. This is a unipotent radical. Modulo that you have some Levy, and you have the center of this Levy and semicircle part.
Oh,
Okay? The semicircle part, when P is a minimal parabolic, is compact. And you can, I don't know, let's change its name to H. You can just take A and N, and it is still compact. The minimal parabolic is compact. It's co-projective. And it's a minimal such. And this is co-compact, and this is minimal group, which is co-compact. Minimality means this thing. So this is how you may think of those things in practice. Let me generalize this example. So SL2C, by the way, I said it acts conformally on it acts conformally on S2. So you may think of it also as SO31. So S2 is the boundary of the hyperbolic space, hyperbolic free space. The SO31 is the isometric group of the hyperbolic free space. It acts isometrically on the space itself, and it acts conformally on its boundary. More generally, SON1 acts conformally on Sn-1, which is the boundary of Hn. So for whom what I'm saying now is just meaningless. So I will, I don't know to what extent, but I will discuss symmetric spaces. And this is a major example of symmetric spaces. And I will, again, I don't know to what extent, but I will try to touch it pretty soon, I think. But just to illustrate things, and I'm using maybe notions which, I mean, just as an example, I'm allowing myself to explain things which I don't fully discuss. So what's that I want to say about this example? So this is G mod P. P, well, we can define it this way. It's the stabilized on the point in here, maybe the North Pole. P is a parabolic. So this is rank 1 group. So there is a unique parabolic or up to conjugation. The parabolic that is defined over the rings. And P, and again, you can write down P in some coordinates in MAN. So this is SO n minus 2. Oh. Sn minus 1, you may think about it as one point compactification of Rn minus 1, and P is the stabilizer of this infinity. N, the unipotent radical of P, fixes this infinity and is a copy of Rn minus 1, acting by translations here. And now you have the tangent action on the tangent space to this infinity, which is conformal. N acts trivially, and MA is a conformal group of the tangent space. So this is the isometry group of the tangent space, which is n minus 1 dimensional, times R star, times, okay, this is the Rn minus 1 is here. Okay? And this is our A. This is a compact noise. This will be the maximal split soluble group that you see in this group. Okay, so this is for those who know this group from their other lives. This is the H that Tim is talking about. And a subgroup of this one will be compact if and only if it contains a conjugate of this H. And again, the difference between this and the minimal parabolic is this compact noise over here. Which, so this manifold, again, G mod H here, there's a similar description. I don't know if my notation here is standard. This is the projective tangent space. Projective tangent space to Sn minus 1. And it is not a projective variety. But modulo these fibers, it will be. עכשיו וחצי. עכשיו תה? לא יהיה הפעם. לא יהיה הפעם. בגלל ארבע וחצי יש תה לכולם. Okay, so I'll put the corollary there. So corollary to the term. Assume G is already compact. That is, I'm discussing now this theorem in the case of A distribution, this maximal value. So this happens if and only if G has no such groups, right? No K-split GA. Oh, it doesn't have it. In particular, in zero periphery case, it doesn't have any unipotent radical. G is reductive. A group is reductive if its unipotent radical is trivial. Right? So compact groups are all reductive groups. Reductive, so to remind you, no unipotent radical. Here I don't have unipotence at all. In characteristic 0, it means that my group is towed groups by semi-singletons. I have two examples of rotative groups: Torine and semi-single groups, and also whatever I can combine maybe these two. So I have G always have its center and always have its commutator, and it should be the product of these, and these should be semi-simple, and these should be a torus. And maybe they have a finite intersection, these two. An example, GLM. Right? It has one-dimensional torus, it has SLM, and maybe the torus, the one-dimensional torus intersect SLM, depends on the field. If you have root of unity of the dimension, right? In SL2, you have -1, -1, the diagonal group, which is a scalar matrices and center.